Hello everyone, my name is Gong Cheng, and today I'm going to talk about VCSeg virtual camera adaptation for row segmentation. This work is done by me and Dr. James H. Elder. One essential challenge in unsupervised domain adaptation is handling domain shift between the source domain and the target domain. For row segmentation case, we noticed that one of the principal causes of the domain shift is variation in the geometric camera parameters. Commonly, when transferring from the source domain to the target domain, this shift is typically ignored, and the images are resized to a standard size for network training and adaptation. However, for row segmentation, this may result in misregistration of the source structure between images. To address this problem, we argue that the training and inference should be performed not in the native pixel domain of the images, but rather in a standard virtual camera domain. Hence, we proposed a virtual camera method for row segmentation, VCSeg in short, that reduces shift both between and within cameras, leading to more stable and reliable segmentation performance. As in GeoSeg, we use 5 diverse row segmentation datasets for method development and evaluation. Overall, those methods involve driving scenes captured by vehicle-mounted cameras under varying road weather, lighting, and viewing conditions. We collect and approximate average intrinsic and extrinsic geometric parameters for all 5 datasets. Where camera height and tilt were not specified, we were estimated by visual inspection of those images. Following GeoSeg, we train and evaluate in a 5-fold leave one out manner. In each trial of domain adaptation, 4 labeled training sets are employed as the source domain, while the 5th unlabeled test set is the target domain. The overview of our method is shown below. The first step is to define a standard virtual camera with real camera parameters and approximate the mapping from the real to virtual camera planes as a homography. To do this, we employ a world coordinate frame aligned with and lying on the road, directly beneath the camera. Given all the camera parameters, we then project all the images to the vertical ground plane. To preserve the maximum resolution, we set both X and Y focal lengths of the virtual camera equal to the maximum focal length over all the datasets. We next selected the horizontal and vertical FOVs of the virtual camera to ensure that at least the lower half of all physical camera images reprojected to line within the virtual camera image. Combining the above defined FOVs and focal lengths, we then can get the virtual camera resolution. And finally, we employ a central principal point. By projecting individual datasets images to this standard virtual camera space, between camera shift can be reduced. We further update the rotation matrix to reduce the shifts in the extrinsic camera parameters within datasets. After virtual camera projection and shift reduction, gaps will be generated since image projections cannot cover the whole virtual plane. We propose a novel vanishing point-based projective image completion method that fills those gaps in a plausible way. And finally, the network can be trained using the source domain projective completed images. We also try to integrate our projected images with a geometry-driven adaptation method proposed by GeoSeg. A series of experiments have been conducted to verify the robustness and the performance of our method. The average runtime for inferencing one image is shown below. The table below shows the quantitative LU comparison between our VCSegnet and the prior adaptation method, all on a common segnet architecture. We find that our between-camera reprojection method leads to a dramatic improvement against the segnet. After adding the within-camera shift reduction, we observe a second dramatic improvement, which makes our LU reaches 71.1% with a 9.8% lead over the prior best method. And here are some segmentation examples. We also compare against 2 more recent pre-trained semantic segmentation networks with different architectures. For more details about our work, please review our paper. Thank you so much for listening.